Hello, everyone. My name is Gyeongsik, a postdoctoral associate at Korea University. This work has been completed with my colleagues, Changyong Shin, Yeonho, and Professor Chuck Yu. Our paper, which presents a case for SDN-based network virtualization, introduces the performance benchmarking of a new network virtualization technique. Recently, various services such as iCloud, Netflix, and GE's user services have pre-matured in our daily lives. And most of these services are operated on public clouds, such as Amazon's AWS and Microsoft's Azure. Each service is considered as a tenant, and each tenant creates a desired computing resources, such as virtual CPU, virtual memory, and virtual I/O resources. Then such resources are converted into a form of virtual machines or containers that consist of several services. Nowadays, especially container-based virtualization is being used as a de facto technology. And according to the IBM in 2020, 61% of enterprises using the cloud have used containers more than half of the time over the past 2 years. And more than 79% of enterprises recognize the importance of containers. When containers are created for each tenant, the network connection should be provided between the containers. Also, in the cloud, multiple tenants coexist, so their network connection should be isolated from one another. The technology for achieving such isolation is called as network virtualization. Network virtualization, which we refer to as NV, provides virtual networks while ensuring the isolation of each virtual network. In the current cloud, network packets created from containers should be differentiated between tenants when the packets are processed by the physical switches in the cloud. In this regard, the current solutions differentiate the packets by two primary methods. The first method is NOT, which rewrites its address of the containers into globally unique addresses. Another technique called overlay or tunneling is used to attach an additional header in front of every packet and assign an ID to differentiate between tenants. All these operations are implemented at the software switches in the servers running containers. Although such solutions will operate on the existing clouds, a major problem with the current network virtualization is that tenants do not have any control over their virtual network, which is called programmability. Programmability here refers to the control authority over the virtual network resources. Consider the computing resources such as CPU, memory, and I/O resources. The user can freely select their desired devices, install and run any program, or monitor the performance bottleneck over them. Similar to them, network programmability includes topology provisioning, direct control over switches, and monitoring. However, the current solutions does not expose virtual switches to the virtual network users. This is a significant drawback for users on virtual networks because the users cannot experience the numerous optimizations made by the SDN. Also, they cannot install their custom network policies or diagnose the service performance bottleneck inside the network. So the solution to this problem is to use SDN-based network virtualization, which we abbreviate as SDN-NB. SDN-NB is a promising technology that provides programmable virtual networks. The key enabler of SDN-NB is the network hypervisor. The network hypervisor is located between the physical network and accepts requests from virtual networks, such as virtual network topology provisioning. For example, the network hypervisor manages a single physical network globally and virtualizes the physical network to multiple virtual networks. The network hypervisor provides the virtual networks to multiple users, and each virtual network controller manages its virtual network as a form of SDN. In this way, SDN-NB allows virtual network users to provision their desired topology and configure their virtual network resources through their SDN controllers. Here, we present a control example of virtual network from tenants. When there is a new traffic such as TCP flows, The network switch alerts the event to the controller, which is the network hypervisor. The network hypervisor then delivers the notification to the corresponding controller. Upon receiving the message, the controller calculates the appropriate policies, which are referred to as flow rules. Such rules are first delivered to the network hypervisor and then installed to the physical switches. Between the controller and physical switches, the network hypervisor translates such messages. In particular, the network hypervisor performs address virtualization. For example, the containers of each tenant can have arbitrary addresses, so the addresses might conflict between the tenants. The network hypervisor in the middle translates any messages between the virtual network and physical network, and such methods are mainly on one of the three, which are address mapping, PID embedding, and locator embedding, which will be explained from now on. So the first method is address mapping. For the sake of distinction, we'll refer to the address randomly used by each virtual network as virtual address. This method uses one-to-one mapping of the virtual network, virtual address to the physical address. This is somewhat similar to the concept of virtual memory in the operating system. The currently used virtual IP is mapped one-to-one to a limited physical IP area, and this mapping structure is stored by the network hypervisor. As presented in the figure here, one physical address is allocated for each tenant and virtual address pair. And these addresses are translated at the first switch where the containers are attached. For example, packets 1 to 2 are converted to Roman letters 1 to 2, and orange tenants are converted to Roman letters 3 to 4. In the middle switches, each tenant's packets are distinguished by the Roman letters. The second method is calling PID embedding, which is the approach of adding an identifier that distinguishes a tenant somewhere in the packet without changing the address itself. For example, in the situation presented here, there is a blue user and an orange user. The left containers have the same IP address as in the slide before, while the right containers have their own same IP address as well. When the packets of these containers come and go, the address is maintained as is. And in addition to this address, separate values such as A and B that distinguish its tenant are written in its packet as well. Then physical switches can distinguish containers based on the A and B values along with the virtual addresses. The third method, called locator embedding, is based on the location of containers. This method embeds the location of containers in each packet header. For example, as presented here, the left container is attached to switch 1 and the right container is attached to switch 4. The packet going from left to right is encapsulated by the source address of switch 1 to the destination address of switch 4. The middle switches forward packets by the addresses of switches 1 and 4. Including such abstractions, various research efforts have been made in SDN-MD. For example, several studies have focused on improving the entire platform scalability to accommodate a larger number of tenants. Additionally, the performance aspects such as the monitoring of VN or the guarantee of throughput of each VN have been investigated. However, the focus of this paper is that the practical values must still be proven, which are the performance and overheads of SDN-NB. We conducted a critical review of the evaluations in previous studies as presented in the table here. In summary, the studies still lack important evaluations, which results in critical limitations for grasping the practicality. Due to the time limit, we deliver only the key limitations in such studies. The benchmarking on SDN-MB can be classified into two categories. First is the performance and overheads of the physical network, such as the throughput or latency of the traffic. The second one is the performance of the network hypervisor, which will be explained later. There are two primary metrics for benchmarking of PN, namely the throughput and per packet latency of individual network flow. Such metrics vary according to the number of virtual networks, physical switches, and number of flows coexisting in the physical network. However, previous studies are lacking in the following areas. First, the performance of the physical network has been measured with only limited experiment variables. For example, there are no changes in flows or only 1 to 10 switches are tested. On the other hand, we have changed the number of switches and flows in various ways. Second, evaluations have been conducted with only a single tenant. In contrast, we perform experiments with up to 20 VNs. Third, and very importantly, physical network evaluations have not been compared with existing network virtualization technologies. Meanwhile, we compare the schemes of SDN-MB, address mapping, TID embedding, and locator embedding to the widely used container technologies, which are not an overlay. We first report the evaluation results of the throughput. We present here only a portion of all the evaluations due to the time limit. So please refer to the complete analysis and experiments in the paper. In terms of the throughput, the overlay of the container exhibits a rather poor throughput, while the other groups maintain regular values. This is because overlay requires that each packet traverse the networking stack of the kernel in the operating system twice to perform packet encapsulation and decapsulation. On the other hand, the other schemes do not require this, so the throughput is different. Second, in terms of the per packet latency, the NAT and overlay demonstrate similar latencies. On the other hand, the schemes of SDN-MB exhibits low latencies compared with NAT and overlay. This is because the SDN-MB schemes are deployed with Open vSwitch, which has better utilization than the kernel-based approach of containers, such as bridges. In addition to the physical network benchmarking, we also perform benchmarking on the network hypervisor as well. There are mainly two metrics for network hypervisor benchmarking, namely the message processing delay, which is the time needed to process a single message between the switch and controller inside the NH, and the CPU cycles of the NH. These two metrics vary in terms of the number of virtual networks, switches, and flows similar to the physical network benchmarking. The benchmarking reported in previous studies has the following limitations. First, previous studies used limited number of experiment variables. In contrast, our paper increases the number of switches and flows to 100 and 200 respectively. Also, we perform experiments using multiple tenants up to 70. Finally, the previous studies involved somewhat out-of-date solutions, such as the APIs and syntax of the messages between the physical switch and controller are defined as a protocol in SDN-MB. The previous studies reflected only the past versions, such as OpenFlow 1.0. In contrast, we evaluate using OpenFlow 1.3 with recent network hypervisor and compare the three address virtualization schemes similar to the physical network benchmarking. Note that the benchmarking on network hypervisor compares between only the three address virtualization schemes in the SDN-MB without comparison to the containers. This is because the container does not have any NH, so the measurements cannot be conducted on the containers. So we first explain the evaluations results for the message processing delay. In terms of the packeted message used for a switch to report that a new flow has been generated, address mapping and TID embedding exhibit constant delay near 1 millisecond. However, locator embedding exhibits delays that are 2 times longer. The reason for this longer delay is due to the lack of optimization in locator embedding in the current network hypervisor. We found that the implementation of locator embedding in network hypervisor distinguishes between the flow rules coming from controllers based on the per host. However, if the virtual network controller creates flow rules per apps, such as TCP pairs, multiple sets of flow rules can exist per one host pair. Such rules are ruined, and installation is repeated in NH. During this repetition, the switches repeats the notification of the new packets because the rules for processing the new packet have not been installed. We additionally optimized the implementation of locator embedding by making the NH to cover the flow rules per apps as well. This optimization resulted in the packet delay to be reduced in a 1 millisecond level, which is similar to the locator embedding and PID embedding in the results before. The CPU cycle required for processing packet message also reduces, as the figure shown in the right side. Second, we consider the delay for processing the message to install flow rules. In the result, the processing delay decreases by up to 39%, 41%, and 23% when the number of VNs increases. This is somewhat surprising because the increasing number of virtual networks could cause the network hypervisor to overload. The reason for this result is as follows. In our experiment, the number of TCP flows existing in the physical network is identical for all cases. Therefore, when the number of virtual networks increase, the flows to be processed by each virtual network decreases. The number of flow rules per each virtual network accordingly decreases, and NH internally, NH contains several lookup processes. For example, NH lookups the previous installed flow rules for maintaining the consistency between physical network, network hypervisor, and the controllers. Also, NH finds the virtual and physical addresses for performing the address virtualization. The decreasing number of flows causes the overheads of lookup to decrease. So in turn, the delay for message processing likewise decreases. We also present the CPU cycle when the number of switches increases. The CPU cycle increases from 10 to 60 switches and then demonstrates somewhat constant CPU cycles. It is natural to expect the CPU cycle to increase as the number of switches. However, the CPU cycle saturates at around 60 switches. The reason for this is that the CPU cycle is primarily used for topology discovery. Topology discovery is for echoing switches regularly for updating physical network topology. The size of the echo messages between the network hypervisor and switches is less than the 200 bytes, and they are communicated within 100 milliseconds on average. These kinds of communications are considered to be short-lived connections. In fact, in modern operating systems like Linux, when the number of short-lived connections, especially for TCP, increases, the processing becomes bottlenecked. So in our experiment, the CPU cycle is dominated by the kernel of the operating system, not by NH. The saturation point was the 60 switches. As a result, the CPU cycle yields the following results. So this brings us to the conclusion. In this paper, we comprehensively investigated the performance and overheads of SDN-MB. Through experiments, we revealed that SDN-MB can demonstrate better performance in switches than can the container technologies. Also, for the overheads, the memory processing delay or CPU cycles in the network hypervisor remain mostly constant as the various variables increase. Moreover, we found that the network hypervisor can reduce the message processing delay when the number of tenants rather increases by decreasing the overheads imposed on the individual virtual networks. So that concludes the presentation on our paper. Thank you for your time.